Earlier we talked about an ideal D2C converter. It converts a discrete time sequence y of n to a continuous time signal yr of t. And the ideal D2C converter can be viewed as having two parts. The first part is a sequence to impulse train, and the second part is a ideal low-pass filter, HR. For example, as an example, suppose this is the Fourier transform of y, the sequence y. So it's discrete time Fourier transform, and the height this is 1. And the reconstructed signal yr of t, it's a continuous time signal, it's a Fourier transform, it's going to have the same shape as y, but it's a frequency scaled version. Now it's non-zero between minus pi over t to pi over t, and the height here is t. So this is the case when we have an ideal D2C converter. But in practice, this is not how it usually works. Now let's talk about a more practical D2A converter. A more practical D2A converter converts a discrete time sequence yn to a continuous time signal y dat. This is a D2A converter, digital to analog converter. Digital to analog converter, D2A. And we put DA as a subscript to indicate that it's the output of a D2A converter. So what does a D2A converter do? Suppose this is our input sequence yn. Yn is this example here. And the D2A converter will hold the value of y hold the value of each sample for a period of t. Okay, so at time 0, this samples come in and it's going to hold its value for a period of t. And for the next n, it's going to hold it for a period of t, and then hold this sample for a period of t, for this sample for a period of t. So this is what the output of a D2A converter look like. Okay, first of all, it's going to hold the value y0 for a period of t, and then y1 for a period of t, and then y2 for a period of t, and then y3 for a period of t. This is 0, t, 2t, and 3t. Okay, so it's like this. So the output has a staircase or a stair-step shape. So this is a staircase. Or it's a stair step. Now let me ask you a question. Does the output of the D2A converter look like the signal, the continuous time signal that we would like to have? Do you think it look like the type of signal that we would see for a continuous time signal? So would our continuous time signal look like a staircase in general? No, usually it looks more like a smooth curve. So the output of the D2A converter is not what we want it's not what we want from a ideal reconstruction filter. So what can we do? So what we do is that we pass this D2A converter, pass the output of the D2A converter through a reconstruction filter, but this time we have a tilde, Tilde, tilde. We pass it through a tilde filter. And what is the role of the tilde filter? We would like the tilde filter be designed so that this is equivalent to the D2A converter. We would like to be equivalent to the D2A converter. I'm sorry, the D2C converter. The D2C converter. Okay, and remember this D2C here, this is discrete. So let me put discrete. This D2C converter, the D here is discrete. That's what it means, discrete to continuous time converter. And this D here is digital. Okay, so both of them are D, but they means different things. So how can we would like to design this reconstruction filter, compensate the reconstruction filter so that it will look like the ideal D2C converter? So now that's the question. How do we design the compensated reconstruction filter HR tilde? And for this, we need to first answer the question of how is YDA of T related to YN. We know how it looks like, how they are related in picture, but can we find a mathematical expression to describe their relation? And for the design matter, usually we do it in the frequency domain, right? So we would like to know how YDA J omega is related to the Fourier transform of the Y sequence. To see how YN and YDA are related, let's go back and examine the figure again, their plots again. Let's observe that if we look at YDA in an interval of T, then we see what does it look like just for this interval of T from 0 to T. What does it look like? It looks like a rectangular pulse, doesn't it? And now if we look at between T to 2T, what does it look like? It's another rectangular pulse. It's just shifted and the height is different. And again, look at between 2T and 3T, we get the rectangular pose. Again, shifted and with a different height. So if we want to describe Yn and Yda mathematically, what can we do? Let us define a rectangular pose. Between 0 and t is equal to 1 and 0 otherwise. And the picture of h0 would look like this. Between 0 and t is equal to 1. And it's 0 otherwise. This is h0 of t. Now let's try to use h0 of t to describe a Yda. Yda of t, between 0 and t, it will be y0, its height is y0, y0, and it's the rectangular pose h0, h0 of t, right? And between t and 2t, what is this? That would be between t and 2t, it would be rectangular pose h0, but with a shift. How much is the shift? It's shifted by t, and the height is y1. Similarly, for the next 2t to 3t interval, it will be h0, t minus 2t, and the height is y2. Continue on like this. And for the other side too, it will be y0, y minus 1, and h, t plus t. And for the other side too. So if we want to write it in a more compact form, then what we have would be Yn, and then t, h0, forgot an h0 here, Yn h0, t minus and t, and summation over all n. Does this look familiar? Does this expression look familiar? Have we seen something like this before? This continuous time signal that is a sum of shifts of a certain function, and each shift has a different weight. We have seen something like this before, right? Where have we seen it? Does this look like the output of a D2C converter? A D2C converter? But at that time, H0 is replaced by HR. That's the only difference, right? H was HR, T minus NT. That is the output of a D2C converter. With a D2C converter, YR of T is summation Yn HR T minus NT summation over N. And we compare this with the expression of the D to A converter output that we just have. Then we see they are exactly the same, except that HR is replaced by H0. So how can we see a D to A converter? It can be viewed, a D to A converter can be viewed as like a C to A, like a D to C converter. It has two parts. The first part is a sequence to impulse train, and for the second part, it's not HR anymore, it's H0 J omega. Input Y0 and output is Y DAT. So the cascade of the D2A and HR tilde can be viewed like this. It can be viewed like this. It can be viewed as because D2A now has two parts. One is H0. This is H0 J omega. And this is, the last one is HR tilde. And the first one, D2A, the first part of D2A converter is a sequence to impulse train. Impulse train. Input YN and the output of H0 J omega is Y DAT. Now if we would like the cascade of these three all together to be the same as D2C converter, what can we do? Compare this with the two parts of D2C converter, and we know what should these two filter, the cascade of these two filter be? What should it be? If we can design HR tilde so that the product of the two to be the same as the ideal reconstruction filter, then we are done, right? If we can do that. So we should choose HR so that their product is the same as HR J omega. In other words, that means HR J omega should be 1 over H0 J omega. And for the range, omega is in this range and it's 0 elsewhere. If we choose HR like this, then what does it look like? We know H0 is the rectangular pulse, right? And its Fourier transform can be derived. Its Fourier transform is equal to E minus J omega t over 2 sine omega t over 2 and then omega t over 2. It's like a sinc function in the frequency domain. So if we draw the magnitude response, it will simply be t and sine omega t over 2 and omega t over 2. And what kind of function is this? If we look at the numerator, it will come to 0 crossing at 2 pi over t. The curve will be like a sinc function, right? And it's a 0 crossing will be at 2 pi over t. Because if you substitute in 2 pi over t in here, omega is equal to 2 pi over t, then this is pi, and then you get 0. The sine function will get 0 in the numerator. And that's what it looks like. In the frequency domain, H0 J omega magnitude. And this is minus 2 pi over t. And the height here is t. This is the Fourier transform of H0. And HR will be the reciprocal of that for the range between minus pi over t to pi over t. So it's here, this part, the reciprocal for this part, only for this part. So we can draw that as well. If we draw HR tilde j omega, then it will be 0. And then pi over t to minus pi over t, because this is the range of HR tilde. And because if we look at the curve here, it's like this. When you take the curve here, it's shaped like this. First it's down, and then up, down, and then up, and then down again. So when you take the reciprocal of the value of HR, then you get a curve that looks like this. Slightly shaping like this. And that's the, if you look at them, that's the magnitude part of HR, J omega. And this is omega as well, H0 J omega magnitude. Oh, let's not forget that HR has the IQ reconstruction filter has a height T. So, here, this HR has a height T. So here it should be T. It should be T here. Okay, and then here is a T. Here's a T here. So when you take T divided by T, so the value here will be 1.